Ground fault protection is required for systems with voltages above 150 volts to ground because the higher the voltage, the greater the potential for electrical shock and injury. Therefore, this protection is implemented to minimize the risk of electrical shock. It is not safe to not have ground fault protection for any system regardless of voltage or amperage. Ground fault protection is required for all electrical systems to prevent electrical shock and injury. There have been numerous studies on the effects of ground fault for system voltages of 240 V/139 volts. These studies have demonstrated that ground faults can cause serious electrical shock and injury. Reference materials that provide an explanation of the provision requiring ground fault protection for systems with voltages above 150 volts to ground include firstly NFPA 70, E standard for electrical safety in the workplace, and secondly IEEE 1584 guide for performing arc flash hazard calculations. Let's delve deeper into the specifics of ground fault protection. A ground fault occurs when an unintentional electrical path is established between a live conductor and ground. This can happen due to damaged insulation, equipment failure, or accidental contact. The resulting current flow through the ground path can be dangerous, posing a significant risk of electrical shock to anyone who comes into contact with the energized equipment or grounded surfaces. Ground fault circuit interrupters, or GFCIs, are designed to detect these ground faults and quickly interrupt the power supply, thereby minimizing the risk of electric shock. GFCIs work by monitoring the current flowing in the hot and neutral conductors of a circuit. Under normal operating conditions, these currents should be equal. However, if a ground fault occurs, some of the current will flow through the ground path, creating an imbalance between the hot and neutral currents. When the GFCI detects this imbalance, it trips the circuit, cutting off the power supply in a fraction of a second. The National Electrical Code, or NEC, provides specific requirements for ground fault protection in various types of electrical systems. These requirements are based on the voltage to ground, the amperage of the circuit, and the type of occupancy. For example, the NEC typically requires ground fault protection for 208 volts or 277 volt circuits that supply receptacles in commercial and industrial locations. The NEC also requires ground fault protection for circuits that supply equipment in hazardous locations, such as those containing flammable materials. The purpose of ground fault protection is not only to protect people from electrical shock, but also to prevent equipment damage and fires. Ground faults can generate significant heat, which can damage equipment and ignite flammable materials. By quickly interrupting the power supply, ground fault protection can minimize the risk of these hazards. Now let's consider the specific scenario of a 240 V/139 volt system with a main disconnect rated at 1000 amps and above. In this case, ground fault protection is definitely required. Although the voltage to ground, 139 volts, is below the 150 volts threshold that triggers mandatory ground fault protection in some specific applications, the high amperage of the main disconnect necessitates its implementation for overall safety and code compliance. Even though the voltage is slightly below the threshold in certain NEC sections, the potential for a high current ground fault event in a 1000 amp system presents a significant hazard. A ground fault in such a system can result in a massive release of energy, leading to arc flash, equipment damage, and potential injury. The ground fault protection system will detect the ground fault and trip the main disconnect, minimizing the duration and magnitude of the fault current. Now let's turn to the reference materials. NFPA 70. E Standard for Electrical Safety in a Workplace provides comprehensive guidance on electrical safety practices, including ground fault protection. This standard covers a wide range of topics such as arc flash hazard analysis, personal protective equipment, and safe work procedures. NFPA 70. E emphasizes the importance of ground fault protection as a critical safety measure for protecting workers from electrical hazards. IEEE 1584 Guide for Performing Arc Flash Hazard Calculations provides a method for calculating the incident energy and arc flash boundary for electrical equipment. This standard is used to determine the appropriate level of personal protective equipment required for workers who may be exposed to arc flash hazards. IEEE 1584 also recognizes the role of ground fault protection in reducing the severity of arc flash events. In addition to these standards, there are numerous other resources available that provide information on ground fault protection. These resources include manufacturers' literature, industry publications, and online training courses. It is important to stay informed about the latest developments in ground fault protection technology and best practices. In summary, ground fault protection is an essential safety measure for electrical systems of all voltages and amperages. It protects people from electrical shock, prevents equipment damage, and reduces the risk of fires. Ground fault protection is particularly important in high current systems, where the potential for a hazardous ground fault event is significant. NFPA 70 and IEEE 1584 provide valuable guidance on ground fault protection and other electrical safety topics. Now, to expand further on the topic, consider the different types of ground fault protection systems available. There are primarily two main types: firstly, ground fault circuit interrupters, or GFCIs, and secondly, ground fault relays, or GFRs. GFCIs are typically used for protecting individual circuits or receptacles, while GFR are used for protecting entire electrical systems. GFCIs are self-contained devices that directly interrupt the circuit when a ground fault is detected. They are commonly found in homes, offices, and other commercial buildings, typically installed in bathrooms, kitchens, and outdoor areas where there is a higher risk of electric shock. GFRs, on the other hand, are more complex systems that consist of a current transformer, a relay, and a circuit breaker. The current transformer monitors the current flowing in the electrical system, and the relay trips the circuit breaker when a ground fault is detected. GFR are typically used in industrial and commercial facilities to protect large electrical equipment such as motors, transformers, and switchgear. Another important aspect of ground fault protection is coordination. Coordination refers to the process of selecting and setting ground fault protection devices so that they operate in a coordinated manner. The goal of coordination is to ensure that the ground fault protection device closest to the fault will trip first, minimizing the impact on the rest of the electrical system. Proper coordination requires careful consideration of the characteristics of the electrical system, the available ground fault protection devices, and the applicable codes and standards. In addition to the types of ground fault protection systems and coordination, there are also several other factors to consider when implementing ground fault protection. These factors include the grounding system, the bonding system, and the surge protection system. The grounding system provides a low impedance path for fault current to flow back to the source, which helps to ensure that ground fault protection devices will operate quickly and effectively. The bonding system connects all of the metal parts of the electrical system together, which helps to prevent voltage differences between these parts and reduces the risk of electric shock. The surge protection system protects the electrical system from voltage surges, which can damage equipment and cause ground fault protection devices to malfunction. When selecting and installing ground fault protection devices, it is important to follow the manufacturer's instructions and the applicable codes and standards. It is also important to regularly test ground fault protection devices to ensure that they are operating properly. Testing can be performed using a ground fault tester, which simulates a ground fault and verifies that the device trips correctly. In conclusion, ground fault protection is a critical safety measure that protects people from electrical shock, prevents equipment damage, and reduces the risk of fires. It is important to understand the different types of ground fault protection systems available, the principles of coordination, and the other factors that can affect the performance of ground fault protection. By following the manufacturer's instructions and the applicable codes and standards, you can ensure that your electrical system is properly protected from ground faults. To further elaborate, let's discuss the specific requirements for ground fault protection in different types of occupancies. The NEC provides different requirements for ground fault protection depending on the type of occupancy, such as residential, commercial, or industrial. In residential occupancies, GFCIs are required for receptacles installed in bathrooms, kitchens, and outdoor areas, as well as for circuits that supply certain appliances, such as dishwashers and washing machines. These requirements are intended to protect homeowners and their families from electric shock in areas where there is a higher risk of water contact. In commercial occupancies, GFCIs are required for receptacles installed in bathrooms, kitchens, and other wet locations, as well as for circuits that supply certain types of equipment, such as swimming pool pumps and hot tub heaters. GFR may also be required for large electrical equipment, such as motors, transformers, and switchgear. The specific requirements for ground fault protection in commercial occupancies depend on the size and type of the facility. In industrial occupancies, GFR are typically required for large electrical equipment such as motors, transformers, and switchgear. GFCIs may also be required for receptacles installed in wet locations or areas where there is a higher risk of electric shock. The specific requirements for ground fault protection in industrial occupancies depend on the type of industry and the hazards present. In addition to the specific requirements for different types of occupancies, the NEC also provides general requirements for ground fault protection. These general requirements include the following. Firstly, ground fault protection devices must be listed and labeled for their intended use. Secondly, ground fault protection devices must be installed in accordance with the manufacturer's instructions. Thirdly, ground fault protection devices must be tested regularly to ensure that they are operating properly. Fourthly, ground fault protection devices must be maintained in good working order. It is important to note that ground fault protection is not a substitute for proper wiring practices. Ground fault protection is designed to protect people from electric shock in the event of a ground fault, but it cannot prevent ground faults from occurring in the first place. Proper wiring practices, such as using the correct wire size, making secure connections, and protecting wires from damage, are essential for preventing ground faults. It is also important to be aware of the limitations of ground fault protection. Ground fault protection devices are designed to trip when a ground fault occurs, but they may not trip if the fault current is below the trip threshold. The trip threshold is the amount of current that must flow through the ground path in order for the device to trip. The trip threshold is typically set at 5 mA for GFCIs and 30 mA for GFR. If the fault current is below the trip threshold, the ground fault protection device will not trip, and the person may still receive an electric shock. To mitigate the risk of electric shock from low-level ground faults, it is important to use other safety measures, such as wearing insulated gloves and using insulated tools. It is also important to be aware of the potential for nuisance tripping. Nuisance tripping occurs when a ground fault protection device trips for no apparent reason. Nuisance tripping can be caused by a variety of factors such as electrical noise, voltage fluctuations, and faulty equipment. To minimize the risk of nuisance tripping, it is important to use high-quality ground fault protection devices and to properly install and maintain them. In addition to the technical aspects of ground fault protection, it is also important to consider the human factors. Human factors refer to the psychological and behavioral aspects of electrical safety. Human factors can play a significant role in the occurrence of electrical accidents. For example, workers who are fatigued, stressed, or distracted are more likely to make mistakes that can lead to electrical accidents. To improve electrical safety, it is important to address human factors through training, education, and awareness programs. These programs should teach workers about the hazards of electricity, the importance of following safety procedures, and the proper use of personal protective equipment. In addition to the information provided above, let's address some additional considerations. Firstly, regular inspection and maintenance of electrical systems are crucial. Electrical systems should be inspected regularly by qualified personnel to identify potential hazards and ensure that all components are in good working order. Maintenance should be performed on a regular basis to prevent equipment failures and ensure that ground fault protection devices are functioning properly. Secondly, arc flash studies are recommended for complex electrical systems. An arc flash study is a comprehensive analysis of the potential arc flash hazards in an electrical system. The study identifies the areas where arc flash hazards are present and recommends measures to mitigate these hazards, such as installing ground fault protection, upgrading equipment, and implementing safe work practices. Thirdly, training and education are essential for electrical workers. Electrical workers should receive comprehensive training on electrical safety, including ground fault protection. This training should cover the hazards of electricity, the proper use of personal protective equipment, and the procedures for working safely on electrical equipment. Fourthly, public awareness campaigns can help to promote electrical safety. Public awareness campaigns can educate the public about the hazards of electricity and the importance of following safety precautions. These campaigns can also promote the use of ground fault protection devices in homes and businesses. Fifthly, collaboration among stakeholders is essential for improving electrical safety. Collaboration among stakeholders, such as electrical contractors, manufacturers, utilities, and regulatory agencies, can help to identify and address electrical safety challenges. This collaboration can lead to the development of new technologies, improved safety standards, and more effective training programs. Let's also cover testing procedures. Regular testing of ground fault protection systems is vital to ensure their proper functionality. GFCIs should be tested monthly by pressing the test button on the device. If the GFCI trips, it is working correctly. If it does not trip, it should be replaced immediately. GFR should be tested periodically by qualified personnel using specialized testing equipment. These tests verify that the GFR is detecting ground faults and tripping the circuit breaker as designed. The testing frequency should be based on the manufacturer's recommendations and the applicable codes and standards. Detailed records of all testing and maintenance activities should be maintained to track the performance of the ground fault protection system. Regarding troubleshooting, if a ground fault protection device trips frequently or unexpectedly, it may indicate a problem with the electrical system. Troubleshooting should be performed by qualified personnel to identify and correct the cause of the tripping. Common causes of nuisance tripping include faulty equipment, loose connections, and electrical noise. The troubleshooting process may involve visual inspection, electrical testing, and component replacement. It is important to follow safe work practices during troubleshooting to prevent electrical shock and other hazards. If the cause of the tripping cannot be identified, it may be necessary to consult with a qualified electrical engineer or a ground fault protection specialist. Let's further explain ground fault protection with more considerations. Proper documentation is essential for maintaining a safe and reliable electrical system. Documentation should include detailed drawings of the electrical system, including the location of all ground fault protection devices. It should also include the manufacturer's specifications for the ground fault protection devices, as well as records of all testing and maintenance activities. The documentation should be readily available to qualified personnel who are responsible for maintaining the electrical system. Furthermore, ongoing research and development are continuously improving ground fault protection technologies. Manufacturers are developing new and improved ground fault protection devices that are more sensitive, more reliable, and easier to install. Researchers are also exploring new techniques for detecting and preventing ground faults. Staying abreast of these advancements is essential for ensuring that electrical systems are protected with the latest and most effective technologies. Let's also consider the economic aspects of ground fault protection. While ground fault protection does involve an initial investment, the long-term benefits far outweigh the costs. Ground fault protection can prevent costly equipment damage, reduce the risk of liability claims, and improve worker safety. The cost of a single electrical accident can be substantial, including medical expenses, lost productivity, and legal fees. Ground fault protection can help to minimize these costs and protect the financial well-being of the organization. Let's consider a practical example. Imagine a manufacturing facility that uses a 480 volts electrical system to power its equipment. The facility has installed ground fault protection on all of its major electrical circuits. One day, a worker accidentally damages a power cord on a piece of machinery, causing a ground fault. The ground fault protection system immediately detects the fault and trips the circuit breaker, cutting off the power supply. The worker is not injured and the equipment is not damaged. Without ground fault protection, the worker could have been seriously injured or killed, and the equipment could have been destroyed. The cost of the ground fault protection system was a small price to pay compared to the potential consequences of the accident. To add another point, let's mention the significance of surge protection. While ground fault protection safeguards against ground faults, surge protection defends against voltage surges caused by lightning strikes, utility switching, or internal equipment. Surges can damage or destroy electrical components, including ground fault protection devices. Therefore, a comprehensive electrical protection strategy should include both ground fault protection and surge protection. Surge protection devices, or SPDs, divert excess voltage away from sensitive equipment, preventing damage. SPD should be installed at the main electrical panel and at individual equipment locations to provide comprehensive protection. Integrating surge protection with ground fault protection enhances the overall reliability and safety of the electrical system. In addition to SPD, proper grounding and bonding are crucial for surge protection. A well-designed grounding system provides a low-impedance path for surge currents to flow to ground, minimizing the voltage stress on equipment. Bonding connects all metal parts of the electrical system together, creating a common ground reference and preventing voltage differences that can damage equipment. Proper grounding and bonding, combined with surge protection, create a robust defense against voltage surges. Let's discuss another practical example. Consider a commercial building with a sensitive electronic equipment such as computers, servers, and telecommunications systems. The building has installed both ground fault protection and surge protection. During a thunderstorm, a lightning strike hits the building's electrical system. The surge protection devices divert the excess voltage to ground, preventing damage to the electronic equipment. At the same time, the ground fault protection system is ready to trip if any ground faults occur as a result of the surge. The combination of ground fault protection and surge protection ensures that the building's electrical system is protected from both ground faults and voltage surges. One further point, the application of ground fault protection in renewable energy systems is becoming increasingly important. Renewable energy systems, such as solar photovoltaic or PV systems and wind turbine systems, often involve high voltages and currents. Ground fault protection is essential for protecting these systems from ground faults, which can be caused by damaged equipment, environmental factors, or improper installation. The NEC provides specific requirements for ground fault protection in renewable energy systems. These requirements are intended to protect workers, the public, and the equipment from electrical hazards. Ground fault protection in renewable energy systems typically involves the use of GFR or other specialized protection devices. These devices are designed to detect ground faults and quickly disconnect the system from the power grid, minimizing the risk of electric shock and equipment damage. Furthermore, regular maintenance and testing of renewable energy systems are crucial for ensuring their safe and reliable operation. Maintenance should include visual inspections, electrical testing, and component replacement. Testing should include verification of the ground fault protection system's functionality. By following these practices, renewable energy systems can be operated safely and efficiently. Let's conclude by emphasizing that electrical safety is a shared responsibility. Everyone who works with or around electricity has a role to play in preventing electrical accidents. This includes electrical contractors, engineers, technicians, workers, and the general public. By following safe work practices, using proper equipment, and staying informed about electrical safety, we can all help to create a safer electrical environment.